So this is where we left off in the lecture here, talking a bit about bioverification of habitat suitability modeling results and validation. So we did talk briefly about this, about the different outcomes of a model, and whether or not those outcomes could be correct, i.e. yes, depends on this on how the model itself is discretized, both in time and space, the process laws within that model, as well as the parameterization. And so discretization, spatial discretization, you can think of this as, is this a one-dimensional or two-dimensional hydraulic model? How is it represented spatially? Is it what's the resolution, the extent, and is that an accurate representation of whatever phenomena you're trying to model? The process laws could be whether or not you're representing everything in the model. So far we've talked about, say, a spawning habitat model. So that spawning habitat may be driven by hydraulics in the sediment, but it may not represent, for example, in it sort of species interaction or competition for space, any sort of density dependence. So that could be a process law that's missing from the process representation. And then parameterization are sort of the inputs. And so given the discretization of the model, given the process laws, parameterization are, for example, the topography you might feed as a topographic boundary condition for hydraulics, or it could be the roughness parameterization of the bed, or it could be the flow boundary conditions that you feed it. So those would represent the parameterization. And the idea here is that if you get those three things right, then the only possible outcome in terms of replicating reality is that it's true, yes, and we can refer to that as a type 1. Now that's a really nice thing to strive for, but it never happens because it's actually impossible to get these things completely right. And now if you got all these things completely wrong, and then the answer to replicating reality is no, that's a good thing. You got the wrong answer for the right reasons. If the answer is yes, you replicated reality, but you did all these things wrong, that's very, very worrying, because that suggests equifinality. It suggests that there may be more than one combination of inputs or representations that produce the same output. And so that's a situation where you can get yourself in a lot of trouble. And these are all the various combinations of yes on some, no on others. And when these replicate reality incorrectly, we worry. When they correctly do not replicate reality, this is really useful information, because we can pinpoint why are these models not performing the way we expect. And so, of course, if it incorrectly does not replicate reality, that's a real problem. All right, so bioverification, it's a test of your predictions. In the case of these ecohydraulic models that result from coupling 2D results with these habitat suitability curves. And so a bioverification model is one that yields reasonable predictions of habitat availability, which may be then used to do further analyses and look at how, for example, those availability metrics might change as a function of flow. And one of the ways in which you can achieve this is with an electivity index. And so I talked a little bit about this in class. And so what we've got here, let's just think of this little Tetris diagram as an output, spatial output of our habitat model. And let's think of the stars as actual locations where, in this case, let's say fish were found. Say they're spawning reds, okay? And so blue is high quality habitat, red is low quality habitat, clear is non-habitat, and in between we've got green is a little less than blue, then yellow, and then down to red. And so what you can do, an electivity index is a very simple way of sort of normalizing your results, much in the same way we normalized to get a preference curve by availability. And so you have this percent U, and so this is where you take the total number of observations that you have here on the bottom, and then the number that you have in the class I, where I is blue, green, yellow, or red. And so if we have, we can count up, let's say in our red, we've got 1, and so that would go on top, and then the total number of all of the stars would go on the bottom here. And then we look at the availability, so how much of class I, so in this case the red, is there in proportion to the total available area. And if you then take the ratio of those two, you get a value. And if that value is right around 1, then that doesn't represent preference or avoidance. It just means that the observations are distributed in alignment with the availability of that habitat. By contrast, if you have an electivity index much greater than 1, then that means that you have preference. It says even though that there isn't that the individuals are seeking out that type of habitat beyond its availability, and then an electivity index much less than 1, or a little bit less than 1, can indicate tolerance, but if it's much less than 1, then it's avoidance, because even though there's a high availability of a particular habitat, they're actively seeking to avoid it. And then 0 indicates that there's no habitat in a particular class. And so here's some example of electivity indexes, and so we've got the number of stars, so that's the number of reds, and then the percent of stars and the percent of areas, and so we put those into this formula, and we see greater than 1 preferences for the green and blue, and then we see avoidance of the yellow and red, and then the white, there's actually no utilization whatsoever, which is good. That's non-habitat. And so when you're doing these things, you want to make sure that the data that you have actually provides a good test. For example, this would be a trivial sort of prediction where you're basically you're not really making a spatially risky prediction. This is a pretty trivial thing, whereas this is a much riskier prediction. So if you have electivity indexes that suggest high utilization of these very specific types of patches, that gives you a lot more confidence than in this situation, because the availability of that type of patch is everywhere. You can also find the contrasting situations. So this would be a situation in which your model is really performing poorly versus it's performing consistently, and so with your independent empirical observations. So here's a real example. These are Chinook spawning reds in a reach flow is from right to left, and we've got blue as high quality habitat, down to red is non-habitat, white is non-habitat, red is very poor habitat. And then the blacks are where we see fish spawning, and lo and behold, the model does a very good job of sort of discriminating, and we find the vast majority of these things in blue, a few in green, and a very few in yellow. And so this shows basically how that plays out. And so what you have here, this habitat quality on the horizontal, the percent occurrence of those. This is the number of observations in the diagonal hatched column, and then the black is the availability of that habitat. And so we can see that we have this intermediate quality class. We have a peak in terms of its availability, but the peak by far is shown over here for this highest quality habitat. That's where you find the most number of reds. Okay. So why might these models not perform as well as we're seeing in that previous example? Well, if we just take the example of spawning, Knapp and Priestler did a study back in the late 90s where they suggested that these habitat suitability curves only account for about 60% of the variability that they see in observations. And so habitat suitability curves consider things like maybe grain size, velocity, water depth, but they often ignore things like hypertrophic exchange, sometimes water quality, maybe in the form of temperatures included. They ignore sediment transport. They ignore a bunch of basin scale things. They also ignore things like social factors between fish, the size and timing of the run, and the sort of heterogeneity. How close is that patch of habitat with, say, good velocity, depth, and substrate combination? How close is it to energy refugia, predation refugia, etc.? So just show you another example. Here's a place where a bunch of gravel. So this is before gravel was placed, and here's a restoration project where they built a bunch of spawning habitat by placing spawning gravels in the channel here. The habitat shifted, and then accordingly the distribution of reds also shifted post response. This is how the habitat quality works out in terms of one of these models. Before, 60 reds in this little reach, afterwards 88 reds, and the availability of this habitat has, in terms of higher quality habitat, improved with the placement of gravel. And then we see utilization of that habitat. Now, heterogeneity is something I mentioned might be important. Here's an example. So this is a riffle here. These are some riffles with some little structural elements. These are boulders. And what we saw is that you could have a big riffle and it might have hydraulically perfect habitat, but then fish aren't utilizing it. Whereas if there's some sort of structural element that provides, in this case, a shear zone, and so there might be a flow separation point here, and this slower water slack water environment in close proximity to this faster water where they're spawning, this provides a perfect place to conserve energy while spawning. It also provides good predation refugia. If fish get spooked, they can go over here and hide in the cover provided from this rock. And so the benefits of those, we can look at things to see whether or not this sort of close proximity might be utilization of these sort of energy and predation refugia habitats. So here's the same reds, and here's proximity to pools. So you can look like how close are each of these, to a pool, and we can go through and take your original habitat model and kind of play this game. So here's habitat close to a pool. Let's go through and look at some of these other things. Structural cover, we might have things like bank vegetation, large woody debris, boulders, deep pools that all can provide these specific functions. And so there's your reds. This is cover provided by overhanging bank vegetation, so that'd be predation refugia. This is cover provided by large woody debris in orange here. And notice in both these cases how close a lot of reds are to something that provides this predation, and in the case of woody debris, energy refugia. This is energy and predation refugia provided by boulders in yellow. And then this is at least predation refugia, if not also energy refugia, provided by these pools. And so you can see in terms of energy refugia, this is our hydraulic model results. These are flow vectors. Green is faster, red is slower, and you can see these eddies downstream of these particular boulders. And look, this is actually this submerged boulder right here, and washed up on it is a spawned out female Chinook. So some of the weaknesses of these traditional habitat suitability index-based models is the habitat requirements are described by very precise habitat suitability curve functions. You can even if the observations themselves are rather improvised, there's independence of habitat parameters is assumed. That's not it's very rarely the case or true. Also, it's difficult to incorporate new parameters because it might be difficult to actually derive these empirical curves for certain things. For example, proximity to energy refugia is a little bit trickier than just going out and measuring velocity and depth. And you need lots of field data to get reliable curves. Also, the curves themselves are site-specific. So we've developed some software for representing these habitat suitability curves and modeling these things. That'll be available later in the year here. We're using this to model lots and lots of different sites across, in our case, the Columbia River Basin. Okay. So next we'll talk about network extrapolation, but I'll pause this podcast segment right here.